Hello friends, in this video I'm going to answer to the questions of this moving charge and magnetism. Those questions which were asked in AHSEC final examination under Assam Higher Secondary Education Council in 2025. So before we start, please do subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you and help me to grow my channel. And if you want to follow me on Insta, this is my Insta ID OJHALAKHYAZIT123. That's my Insta ID. You can follow me on Insta. So now let's start. So here is the question. In case of an electron moving along a helical path, what determines the pitch of the motion? Now you see, suppose this is the direction of magnetic field. This is the direction of magnetic field. When a charged particle is projected in this direction, its velocity is in this direction, and this angle is suppose theta. Then it takes a helical path like this. Okay, it takes a helical path, right? Because of its two component of velocity, one is along the magnetic field, another is perpendicular to magnetic field. Okay, so here it's gonna be v cos theta and this is v sin theta, right? V sin theta. Because of this vertical component, it will take a circular path, and because of this horizontal component, it will go forward as well. That's why we're gonna see a path of spring-like path. Okay, that is called helical path. So because the charged particle is moving forward as well as moving in circular path, that's why we are going to get helical path, right? And pitch means, now you see, what do you mean by pitch? Suppose this charged particle start moving from this position. Now it is moving in a circular path and as well as it is moving in forward direction. Now here you see, so when it completes one circular motion like this, if there is no any forward motion, then it's supposed to be circular, but as there is forward motion, so that's why it will move like this, right? Okay, so now you see, when it completes one cycle, okay, then the distance it covered by it covered in the direction of the magnetic field. Okay, that means along the horizontal direction. So that distance is called pitch. And now you see, as in this direction, as in this horizontal direction, the velocity is v cos theta. Okay, v cos theta, and or you can say speed in the direction of the magnetic field is v cos theta. And suppose the time period, that means time taken by this charged particle, whatever be the charged particle, it may be electron, it may be proton. Okay, so here they are talking about electron, so we're going to consider electron. Okay, so now you see, let capital T be the time period, that time required to complete one cycle. Okay, and during this time period, what will be the distance covered in horizontal direction with this speed, that is given by speed into time, and that distance is called pitch. Okay, now it is seen clearly that pitch depends on this the velocity of this electron. So velocity of this electron along the magnetic field, that means along the axis of the helical path. So this will be the axis of the helical path, and the time period, or you can say frequency, because this time period can be written as 1 by frequency, right? So here is the answer, which is determined by the velocity of the electron along the helix, that is v cos theta. So now you see, if you consider the velocity in one direction, in this horizontal direction, its magnitude will be equal to the speed in this direction. Okay, so that's why I am saying here speed as well as velocity, right? Hope you have understood this. So it depends on this velocity along the axis of the helical path, that is v cos theta, and time period t, or you can say frequency, that is 1 by t. Okay, so this is the answer to this question. Okay, now let me go to the next question. So here is the next question. Write the expression for magnetic force F when a charge Q is moving with velocity v, enters a magnetic field B, and and define 1 Tesla. This is a magnetic field, suppose B. Okay, when a charged particle enters this magnetic field, Q with velocity v, then the force exerted by the magnetic field on this will be in a direction which is perpendicular to both v and b. Okay, so that's why the force must be the cross product of this, okay, and into q is scalar quantity, so scalar product of cross product of v and b. So why cross product? We know that when you find a cross product of two vectors a cross b, right, then a cross b, what will be the vector? Suppose a cross b is equal to vector c, then this c vector is always perpendicular to the plane containing a vector and b vector. Now you see, let me explain why this cross product. Okay, let me insert a picture before that to explain it. So here you see, according to Fleming's left hand rule, this second finger or the middle finger, if it represents the current means, suppose this is a positive charge moving in this direction, so we used to consider the direction of current is the direction of the flow of positive charge, right? So in this direction and with velocity v, and the first finger will represent the magnetic field. This first finger will represent magnetic field B, and we know to apply this Fleming's left hand rule, we have to stress all the three fingers mutually perpendicular. This is perpendicular to this one is perpendicular to this one, right? And this two are also perpendicular as well. So then force will be represented by the thumb. Force will be represented in the direction of the thumb, right? Now you see, this force is perpendicular to both magnetic field and the velocity. And now you see, we know that if you take two vectors a and vector b, and if you find a cross product of these two vectors, then their cross product will be perpendicular to a cross b, will be perpendicular to the plane containing this a vector and b vector. This will be perpendicular to both a and b, right? So as you see, as if you consider this a vector is now the velocity v vector, and if you consider this b vector as the magnetic field, and then force according to the Fleming's thumb left hand rule, the force should be in this direction. So that's why here you see force is perpendicular to both velocity and b, so it must be cross product of v and b. Okay, it must be cross product of v and b, and as the charge is q, so that's why q should be multiplied with v cross b. And if you consider unit charge, then it should be v cross b if you consider 1 coulomb charge. Okay, and for q coulomb charges, it should be q v cross b, right? So hope you have understood this. Q is the scalar here, so that's why we don't need to write here vector. Okay, so hope you have understood what is the reason behind the cross product. Okay, so now let me remove this picture. Now you can pause the video and you can note the answer, right? Let me just give me a second. So here is the expression for the force on the electron. So what is given here? On a charge moving in a magnetic field with velocity v. Now you see, we need to define 1 Tesla from this expression. Now if you see in this expression, if you put here 1 coulomb charge, 1 unit charge, velocity is 1 meter per second, then if you get the force 1 Newton, then we can say the magnetic field is 1 Tesla. If you take the magnitude of this vector, magnitude of this, that must be magnitude of v cross b, q into v cross b, q into magnitude of v cross b, and magnitude of that v cross b is vb sine theta. So here one more condition, this theta must be 90 degree, then you will get 1 Tesla. Okay, when you will put 1 unit charge, that is 1 coulomb, when you will put the velocity 1 meter per second, and when you will put theta equal to 90, then if you get the force is equal to 1 Newton, then we can say this magnetic field is 1 Tesla. So from this relation, you can see, let me clean it, from this relation that F is equal to q v b sine theta, from this relation we can simplify, we can obtain this b is equal to F by q v sine theta. If you put here 1 Newton, and if you put here 1 coulomb, if you put here 1 meter per second, right, and if you put here theta, so that means how will you write the now let me tell you how to write the definition. So from this expression we can write the definition. I will show you how to write, but let me explain first. So you see, if in a magnetic field, a magnetic field is said to be 1 Tesla when a charged particle enters the magnetic field at right angle. So here theta equal to 90, right, at right angle, with velocity 1 meter per second, okay, and if the charge is 1 coulomb, if the charge is 1 unit charge, 1 coulomb charge, and if it experience force 1 Newton force on this electron due to this magnetic field, then this magnetic field must be 1 Tesla, right? Okay, hope you have understood this. So here is the definition. This is the definition. Magnetic field at a point is said to be 1 Tesla if a unit charge moving with unit velocity at right angle to the magnetic field experiences a magnetic force of 1 unit. Okay, so then the magnetic field is said to be 1 Tesla, right? Now what is the next question? State Ampere's circuital law. Using the law, calculate the magnetic field at a distance r outside an infinitely long wire carrying current I. How does magnetic field depends on the length of the wire? Let me give you the answer. First, let me give you the statement of this law. Okay, let me explain the law first. Suppose suppose you have considered a closed path, and through this closed path you have a wire and it carries current I, suppose. Then let me consider a very small length element dl in this direction. Okay, dl. Okay, now you see, and magnetic field due to this current carrying wire, that will be in this shape, circular shape, if you apply the right hand thumb rule, right? And here this is the suppose magnetic field is suppose B here. Okay, then dot product of this magnetic field, and if you take the dl vector, and if you take the integral, line integral along this closed path, then it is equal to mu naught times of I, that is Ampere's circuital law. Hope you know the meaning of meaning of mu naught, right? So let me give you the statement here. You see, Ampere's circuital law states that the line integral of the magnetic field around any closed path in free space is equal to absolute permeability, that is mu naught, times the net current passing through any surface enclosed by the closed path. Okay, so here is the mathematical expression, right? So now what is the next part of the question? Here you see, next part of the question: using this law, calculate the magnetic field at a distance r outside the infinitely long wire carrying current I. Okay, so here you see, here we have a conductor. This is the conductor. Okay, here you can see this is the conductor. Okay, and this is the axis of the conductor. Here you can see this is the axis of the conductor, and this conductor carries current I, and radius of this conductor I have taken small a. Radius of the conductor is small a. This is small a. Okay, and here we have a point P. This is the point P. Here you can see this point, this is the point P. Okay, and we need to find the magnetic field at this point P, and this point P is at a distance r from the axis of this wire, and this P lies outside this conductor. Okay, that means here r is greater than a, that is this distance r, which is the distance of this point from this axis, is greater than the radius of this wire, right? Hope you have understood this. Now you see, if you apply the Fleming's right hand rule, then if you point your thumb of the right hand in this direction, in the direction of current, then the remaining fingers will be warped around this conductor like this. The remaining finger will be warped around the conductor like this, right? So this will be the direction of the magnetic field. So here you see this circle. I have considered the magnetic field induced due to this current carrying conductor. You have got this thing in class 10, right? That when current flows through a conductor, a magnetic field is set up around it, whose direction is given by the right hand thumb rule. Okay, so according to right hand thumb rule, if this is the conductor, right, if this is the conductor and this is the direction of the current, then if you point your thumb of the right hand in the direction of current, other fingers will be warped around this conductor like this, in this direction. Okay, in this direction. Okay, so that means this on this side, here you see the magnetic field will come out, and in this side magnetic field will be directed into the page. This is out of the page, and on the other side you see, on the other side behind this thing, the magnetic field direction of magnetic field will be upward. That means this is the conductor, this is the top, this is the bottom side, right? So here you see this is top, this is bottom, and this is here you see this is the front side. That means from your side, and this is the opposite side. Okay, right? This is up, down, front, back. Okay, and here you see on that side the magnetic field will be upward. Okay, according to that right hand thumb rule, and in that direction we have considered a very small element, length element dl, and taking this one as a vector. Okay, now you see here. Okay, this I have assumed this circular ring around through the point P of radius r. Okay, radius r. Okay, this point is at a distance r from the axis of the wire. Okay, so according to Ampere's law, line integral of B dot L around this circle, this is called Amperean circle. Okay, around this circle, that must be mu naught times of I. okay, according to Ampere's circuit law. So let me go to the next slide. Okay, now you see this was the diagram. This was the conductor. Current is in this direction, and this is the circular part. Here is the point P, magnetic field B. Okay, and this is the DL. Okay, and this radius is R, this is A. Okay, so now this B dot DL, B dot according to line integral, according to Ampere's law, line integral of B dot DL, that must be mu naught times of I, and B dot DL, so integration of B dot DL means B DL cos theta. Okay, here theta, this direct theta is the angle between B and DL, which is 0 degree here. So that's why here cos theta means cos 0 degree, mu naught times of I. So that's why I have written here B DL cos 0 degree, and cos 0 is 1. And now you see B is constant here, uniform magnetic field, so it can be taken outside. And integral of DL, so as we are integrating along this path, so if you integrate DL, then you will get the circumference of this circle, which is nothing but 2 pi r, right? So that's why we have put here 2 pi r, and from which we will get B is equal to this. So this is the required expression, right? And here B is inversely proportional to R, but from this expression it is clear that B is independent of the length of the wire, right? Okay, so now let me answer to the next question. So here is the next question. A circular coil of 30 turns. There is a circular coil with number of turns. Here you see it consists 30 turns. How many turns? 30. Number of turns is 30. So let me write n is equal to 30. And its radius is 0.8. Its radius is 0.8. Its radius is, sorry, not 0.8, 8.0 centimeter. 8.0 centimeter. Okay, is carrying current 6 ampere. So let me draw here. This is the coil, and its radius is 8.0 means 8 centimeter, and it carries current 6 ampere. Okay, and it is suspended in a uniform magnetic field, so that the if this is the plane of the circular loop, and if you draw a normal to this plane, this normal makes 60 degree angle, 60 degree with the magnetic field. Okay, here it is given 60 degree normal of the coil. The field lines, magnetic field lines, make an angle 60 degree with the normal of the coil, and this magnetic field is 1.0 Tesla, means 1 Tesla. Okay, so these are the informations here it is given. Okay, these are the informations given. So what we have n is equal to 30, number of turns. We have radius of the coil r is equal to 8 centimeter. That means 8 into 10 to the power minus 2, 8 into 10 to the power minus 2 meter. Okay, then we have angle between the normal of the coil and the magnetic field, that is 60 degree. Okay, and also we have the magnetic field is 1 Tesla. Okay, let me go to the next page with this given information. Here is the number of turns in the coil, and this is the radius, and this is the current. Okay, we know that torque acting on a coil is given by this expression. Okay, where n is the number of turns. Okay, I is the current carried by the coil, and this A is nothing but the area of the coil, that is pi r square here in this case, because the coil is circular. Okay, so pi r square, that's why I have written here, instead of A I have written here pi r square, right? Hope you have understood this. So now, so this A is replaced by this pi r square. Okay, so let's put all the values here, given values. Okay, and this 36, 3.14, this is 8 into 10 to the power minus 2 square. Magnetic field is 1 Tesla, sine 60, theta is 60 here. So here theta is equal to 60 degree, that is given. Okay, so putting all those values, we have got this answer 3.13. so what we have got 3.13 Newton meter. This is the torque, right? Now you see what is the next part of this question. On replacing the circular coil by a planar coil of some irregular shape of the same torque is found to be applied, how would you explain the matter? Now what is given, so if you don't change the magnetic field, whatever be the magnetic field here, let me take this magnetic field B, this is 1 Tesla, so keep it 1 Tesla, okay. And the initially in the first case, in the when you have solved this problem, in this question, coil was circular. It is mentioned that coil was circular, okay. Now if you replace this coil by any other coil with irregular shape, okay, with irregular shape, a planar coil. Now you see from this expression of torque, you can see this torque depends on the number of turns in the coil. So if the number of turns in this coil and in this coil, if you keep the number of turns same, and current is also same, and if both the coil carries the same current and both are kept in the magnetic field of same strength, and the area of this coil is equal to the area of this coil, then angle between the normal and the magnetic field remains same. In that case, torque will be same, because this torque doesn't depend on this shape, right? So if you keep the area same, then you will get the same torque, okay. So hope you have understood this. So here is the explanation, so you can pause the video and write the answer, okay. So in the next video, we're gonna answer the questions which were asked in 2024, okay. So thank you for watching. See you in the next video. Bye bye.